So let me continue and let's jump on semaphores. You can find the semaphore objects. These have several different flavors. What the semaphore is and how it works. Let's imagine you have got a parking lot. For example, Avis rental car. This parking lot has 3 spaces for car number 1, car number 2 and car number 3. In the binary example, we have got a parking lot for just 1 car, but when you come and you want to take the car from this parking lot, the parking lot is initially empty. So if you want to do something with the car, you have to wait until somebody puts the car in the parking lot, and then you can take it. So the semaphore effectively can stop you from taking the car if the car is not on the place. The semaphores, when you define them, have an empty parking lot. So there is nothing. And to be able to take the car from this parking lot, somebody else has to give you the semaphore. Has to give you the car into the parking lot. So the binary semaphore is a simple flip-flop telling you whether there is an item and you can take it if it is there. You can't, you are blocked if the car is not in the parking lot. So you can see there exist 2 different functions. One, OS semaphore wait, that causes the appropriate task to wait until there is something in the parking lot. There is as well a function called OS semaphore release that gives the car back to the parking lot. So typically you can use a binary semaphore in the way where you are waiting for some event, for something to happen, and when this happens, some other task releases the semaphore. So this way you are able to get synchronized when something else happens. This is as well a very useful thing when you operate with the interrupts. Our TCP/IP stack is based on this mechanism, and when you receive a packet, you get an interrupt, and this interrupt gives the semaphore, so releases it. And the task waiting for the packet within the TCP/IP reception loop will take the semaphore, and it will process the data guarded by this mechanism. So OS semaphore release gives the car to the parking lot and allows other tasks to operate with that. And OS semaphore wait take the car from the parking lot and leave it empty. That's how the binary semaphore works. So this is the case of a binary semaphore with the semaphore present. If task 2 waits for the semaphore, originally there is nothing, no car in the parking lot. So the task 2 is blocked. Task 1 then releases the semaphore, so it gives it to the parking lot. And task 2, because it waits for it and the semaphore gets present, it will take it away, process it, and in the next loop it will again wait for the new semaphore. Technically, this is implemented as a list of 1 item length. We can create the semaphore with the OS semaphore create, wait for it with a specified timeout, and we can as well release the semaphore with the OS semaphore release. It's a very effective synchronization mechanism. It can be used among different tasks, both on the side who releases the semaphore and on the side who waits for the semaphore, because then the tasks can compete for the semaphore. The counting semaphores are something that gives you more possibilities. So if I define a counting semaphore, I am defining how big the parking lot is. So I can, for example, define 3 or 5 elements, and this is the maximum number of cars I have available. So with the counting semaphore, I can release as many as 5 cars and place them into the semaphore. And when I take the semaphore, I can take as many as they are available, but maximum 5 at a given time. This has one big advantage, because again, in case of a web server, for example, where you have a need for several different threads serving different content in parallel, this helps you to distribute the load. Because whenever you get an HTTP request, you put one semaphore in the queue. And if any handler task is available, it can take it. But by number of elements that are available, maximum 5, you can spawn maximum 5 tasks providing different data to you. So if you define a memory just for 5 tasks, the semaphore, counting semaphore, can limit how many of the threads will be available, so it can limit how much memory you spend on sending these HTTP data. Another thing is, if you, for example, allocate different UARTs for communication or blocks of memory, so the counting semaphore can help you to limit the number of resources up to a given amount and not more. You can define the counting semaphore with a count value, and again you can wait for the standard semaphore with a timeout, and you can release the semaphore, and in case there are spaces in the parking lots, the semaphore release will return OK. But if it doesn't fit inside, it will report an error because the parking lot is full. In this case, I can use 2 different tasks that release the semaphore. So both of them put their own cars in the parking lot, and then the task 3 can consume them one by one. But if you would have more tasks, just 2 of them could request any functionality at the same time from task 3. The counting semaphores are typically useful when you need to limit but still define how many elements in parallel can be taken, executed, provided.